So what is least count? Least count is the smallest measurement that can be done on a measuring instrument. Irregular, it is due to randomness, and I don't know the reasons for it. The reasons for this random error is unknown. Except the last number, all the other digits are called as reliable, and the last digit in the measured value is called as uncertain. Hello students, welcome to this second session on units and measurements from first year PUC Physics. I am Madhu R from the Department of Physics, Vidhyaashram PU College, Mysuru, your Temple of Excellence. Let us begin with this session. Let us recall that in the previous session, we had learnt about measurements, physical quantities, wherein we had divided the physical quantities into three types: the fundamental quantities, the derived quantities, as well as the supplementary quantities, wherein we had taken down the plane angle as well as the solid angle. Yes. Then we studied about units, the three system of units, and we understood that the SI system is presently used worldwide. Okay. Under the SI system, we have 7 fundamental units. As you can remember, we had 7 fundamental units. Okay. And then we understood that for the derived quantities, we have derived units. Okay. Then we understood what are the symbols for those units and what is the rules that are applicable for writing the symbols. Moving on, in today's class, let us try to understand some very important concepts like accuracy, precision, least count, so on and so forth. Let us begin. Now, before understanding accuracy, let us try to understand the scale under which measurement happens. Okay. For example, the weight of an electron is found out, okay, which may be in terms of 10 to the power of minus 27 kg, whereas the weight of a star will be in terms of 10 to the power 55 kg, so on and so forth. Okay. Now, when the range of measurement is so large, I will require accuracy at certain places. To understand that in a better way, let us take this example. You go to an iron shop or a steel shop to purchase steel, the raw steel for construction of a house. Probably you may take around 100 ton of steel. While you are measuring those 100 tons of steel, neither you nor the shopkeeper will be worried if the variation of weight is say around 5 kg. If the variation is 5 kgs, will not be bothered because you are weighing 100 tons. Okay. Suppose scenario 2, you are purchasing some fruits or vegetables for your house. Say suppose you are purchasing 10 kg of fruits. If the variation is 5 or 10 grams, you will not be bothered. 5 grams, you will not be bothered. Let us change the scenario. Scenario 3, you have gone to purchase some gold jewelry. Here, the variation, if it is say 0.001 gram, only then you will say that it is adjustable. Even if it is 0.5 gram, I will say that it is costing me as on today, say around 75,000 rupees. Okay. So you can observe based on the measurement, okay, the accuracy is also varying, or the closeness to measurement will also change. So I have to be very careful that what I am measuring and what is the accuracy required. So let us check what is accuracy. Accuracy refers to how close a measured value is to the true value. Suppose you have a quantity which is actually 10 kg in weight. Now you are measuring that with the help of a weighing scale. It shows that it is 9.95 kg. It is quite close. I can say that it is quite accurate. Okay. So what is accuracy? It is the comparison between the measured value to the true value of any object. Okay. So this is called as accuracy, how close you are to the true value. Now coming to another important term called as precision. Let us see what is precision. Precision refers to how close repeated measurements are to one another. I told you in the previous example that an object weighs 10 kg. I have measured it and it has given me a reading of 9.95. I am somehow not convinced. I want to check it twice or thrice. What do? For another measurement, it gives me 9.91. I take another measurement, it gives me 9.89. I take another measurement, it may give me 10.1, so on and so forth. Which means that how close these 4 or 5 readings are to one another. If they are very close to each other, then I can say that the measuring instrument is precise. Okay? You can take one more example for this. Suppose you are riding your two-wheeler actually at 60 kilometers per hour. If the speedometer shows 60, then it is accurate. Okay? Now I want to check the precision. What do? I check the speed 4 or 5 times with a gap of 2 or 3 minutes. What do? I get readings somewhat like this. One reading says 59, another reading says 61, another reading says 58.5, another reading says 59.5. Okay, another reading may say 60.5. So you can check that the variation is between 58.5 to 61. They are not very close to each other. So I will say that the measuring instrument is not precise. Suppose while taking these 5 values, all the time I had got 58.1, 58.2, 58.0, 58.1, 58.0. So this is a very close range. I can say that the measuring instrument or the speedometer is precise, but it is not accurate because the actual speed was 60. The repeated readings are giving me a value of around 58 km per hour. Okay, so that is the concept of accuracy and precision. We can also try to understand this concept with the help of the dart game. Okay, let us take a scenario. One player has sent darts on the board. He has 7 arrows. He has positioned it all over the dartboard. This is neither accurate nor precise. Then we go to player 2. Okay, player 2 hits it in this range. Okay, this is accurate, but this is not precise. This is quite close to the bullseye. Within the red mark itself, I have got 4 arrows. Slightly outside that, I have got 3 arrows. So this is slightly accurate, but this is not precise. Accurate, but not precise. Then I move to player 3. See, none of this is near the bullseye. Nothing is near the bullseye. Everything is almost at the end of the board. But all the 7 arrows are placed very close to each other. So this is precise, but it is not accurate. It is precise, but not accurate. We'll go to player 4. All the 7 arrows are inside this small ring which is called as the bullseye. This is both precise as well as accurate. Okay, so this is how we try to understand the concept of precision and accuracy, which is very, very important in measuring anything. Okay, so whenever we say we try to understand the science of measurement, accuracy and precision is a very, very important concept. Let us move towards the next concept, which is regarding the least count. Now, what does this least count mean? Least count is the minimum measurement that any measuring instrument can make. The smallest measurement that any instrument can make is called as the least count. Suppose you take the ruler. Okay, we all know that we can measure a minimum of 1 millimeter on that ruler or scale. Similarly, on a measuring tape also it is 1 millimeter. The least count of a scale or a measuring tape is usually 1 millimeter. If I want better accuracy, what will I do? I will go to a vernier caliper. The least count here is 0.1 mm. Okay, So the least count is increased. I can get a value of 0.1 mm here. I want further accuracy. What do? I go to a micrometer or a screw gauge. This can ideally give me least count up to 0.01 mm. Okay. So what is least count? Least count is the smallest measurement that can be done on a measuring instrument. Okay. Usually we say that it is the resolution of the measuring instrument or the limit of that specific device. If you ask me what is the limit of a vernier caliper, I say that it can only measure up to 0.1 mm, not beyond. If you ask me the limit of a screw gauge, I say that it is 0.01 mm and not beyond. Along with this, we have got one more concept which is very important with respect to measurement, and that is called the error. It is called as the measurement error. What is the error that is obtained while you are measuring an object? Let us first try to understand what is error. It is the difference between the true value and the measured value. It is the difference between the true value and the measured value, value that you get when you measure an object. Okay. In the previous example, I had told you the true value shown, okay, for a vehicle is 60 kilometers per hour, whereas the speedometer showed it to be around 58.1 or something like that. The difference between these two values is nothing but the error. Okay. Whatever is the true value and whatever is the measured value, the difference between those two will give you errors. We have to understand one thing. Whatever may be the fineness of the equipment, whatever may be the least count of the equipment, we have to always remember that degree of uncertainty or deviation will always remain. You can never measure any object infinitesimally accurately. To the last digit, you can never measure it accurately. Every measuring instrument will have some amount of uncertainty or some amount or degree of uncertainty. Let us try to understand what can be the two types of errors. Okay. Errors are classified into two types, a systematic error and a random error. Systematic errors are generally known to us. We know the cause, why this error is occurring. Whereas a random error is irregular, it is due to randomness and I don't know the reasons for it. The reasons for this random error is unknown. How does the measurement behave under these two errors? Okay, suppose there is no error in the measuring instrument. I have both accuracy as well as precision. The measuring instrument is accurate as well as precise. Now what happens when there is an error? Suppose there is a random error. It means that the measuring instrument is accurate but it is not precise. As you can observe, the same example of dart, all the 5 arrows that this player has put is within the range of the bull's eye, but it is scattered all over it. It is at 5 different places. So there is accuracy, but there is no precision. What will happen if there is a systematic error? Under a systematic error, you can get precise readings, but they will not be accurate. As you can observe here, it is not accurate. It is not close to the bullseye, but it is very precise. All the 5 arrows have been put at the same place. Okay. So what is measurement error? Measurement error is the difference between true value and the measured value. There are two types of errors, the systematic error and the random error. Okay. Let us move on and come to one more important topic called as significant figures. We spoke about accuracy. We spoke about how a measurement is done, so on and so forth. Now let us understand what numbers are important or what numbers are significant when I write down the values of a measured part. Suppose I may say that the length of the table is 1.723 meters. Okay. Now what is important? What is not important? What can be called as a reliable number, what can be called as an uncertain number. This is what significant figures will let us know. Significant figures are the digits in a measurement that carry some meaningful precision. We are more interested in the precision or the preciseness of the value under significant figures. We are interested in the number of digits that are important here. They represent all digits which are known reliably, which means to say that if I am writing that the length of the table is 1.723 meter, generally the first set of numbers except the last number are called reliable, and the last digit in the measured value is called as uncertain. Except the last number, all the other digits are called as reliable, and the last digit in the measured value is called as uncertain. Here, the significant figures indicate the precision of the instrument. How precise the instrument is, that can be understood. Okay. Suppose I write that my weight is 58.5 kg. Here 58 is reliable, 5 is uncertain. Let us try to understand what is this reliable digit and what is this uncertain digit. Under significant figures, every valid measurement consists of two types of digits. They will consist of two types of digits. As I told you, the first set of numbers is called as the reliable digits, and the last digit in the measurement is called as uncertain. Let us take an example. I am measuring the length of a pencil. I am measuring the length of a pencil. If you can observe here closely, okay, if you can observe here closely, the length of the pencil, as I can see there, is greater than 5.6. It is greater than 5.6 centimeter, but less than 5.7 centimeter. It is in between these two values. The length of the pencil is between 5.6 and 5.7. Now the scale is an instrument where the least count is only 1 mm. So I cannot go beyond 1 mm. I cannot say what is its value at 0.01 mm or something like that. So what do? I make an approximation of the last digit saying that it is 5.65 centimeter or 56.5 millimeter. Okay. So when I write that the length of the pencil is 5.65 centimeter, the first two digits here are reliable. As you can see, 5.6 was known to me. They are absolutely certain. I am absolutely certain because they correspond directly to the physical markings on the measuring tool. I can read the measuring tool here and say that this marking is 5.6. There is no ambiguity in that. I am absolutely certain. That is why I call this as reliable. I can rely on this value of the measurement. What about the last digit then? This 0.5 is slightly uncertain. Why? Because I have made an approximation of that. This is the last digit in the measurement. It is always an estimation or approximation of where the measurement falls between the smallest markings. I have the least count. Between the least count markings, wherever they fall, it will always remain uncertain. Whatever is the least count of the measuring instrument, it may go up to 4 digits if you want, 4.7016. This 6 will be uncertain. Please remember, no instrument can measure perfectly infinitely, making the final digit always an educated guess. You know the science of measurement, but you are always guessing it. Okay. So that is where significant figures concept come into picture. Now let us have a look at what are the rules that are there so that we can tell you what are the significant figures in a measurement. Rules for determining the significant figures. There are 5 rules. Let us have a look at them one by one. First rule says all non-zero digits are significant. As I wrote, 1.732 is the length of the table. Here, all 4 digits are significant. If you ask me how many significant figures are there in this number, I'll say there are 4 significant figures. Okay. Similarly, in this example, 2341 meter, there is no zero in this. So all the numbers are significant, 4 significant figures. 14.3 meter is a measurement. There are 3 significant figures, no zeros. Whenever a measured value does not have any zeros, it simply means that all the digits in that measured value are significant, which means that something comes into picture when a 0 digit comes in a measured value. Let us have a look at this. All the zeros between 2 non-zero digits are significant. 0 between non-zero. See, in this 308, 0 is between 3 and 8. So it is significant. 0 between non-zero numbers. 0 here is again between 3 and 8. So it is significant. Whenever a 0 comes between non-zero digits, it is always significant. I can say that 308 has 3 significant figures. 23.08 has 4 significant figures. Okay. Moving on to the next rule. If a number is there without decimal points, or simply I can say for a whole number, a measurement with a whole number, the trailing or terminal zeros are not significant. I have measured something, the last digits are 0. The measurement is a whole number. Okay. Say for example, 12300 meter. The last numbers are zeros, they are not significant. So here it has only 3 significant figures, which are 1, 2 and 3. The zeros are not significant. Similarly, in this figure, there are 3 zeros at the end. There are 3 terminal zeros, which means to say that only 104 is significant, or there are 3 significant figures. Please remember that the 0 between non-zero numbers will be significant. Only the trailing zeros are not significant. Okay. Rule 2 says that zeros between 2 non-zero digits are significant. So in this 0 in 104, okay, is significant, whereas the trailing zeros, the last 3 zeros, are not significant. Okay. So we understood that all non-zero numbers are significant, zeros between non-zero numbers are significant, and in a whole number, the trailing or terminal zeros are not significant. These were the first 3 rules. Let us have a look at the next 2 rules. The 4th rule says that in a number with a decimal point, it is not a whole number, it is a number with a decimal point, terminal zeros are significant. Terminal zeros are significant. Okay. 4.700, terminal zeros are significant. Okay. This has got 4 significant figures. 23.04000, again, terminal zeros in a number with decimal point are significant. Okay. So this number has 7 significant figures. Now, moving on to the 5th rule. I go on to the 5th rule. If the number is less than 1, okay, number is always below 1. So your number will start like 0 point something. When a number is less than 1, zeros on the right of the decimal point. See, 0 on the right of the decimal point, but to the left of the first non-zero digit. So it is between the point and a non-zero digit. These zeros are not significant. These zeros are not significant. If the 0 is at the end, it is significant. But after the decimal point up to a non-zero number, these zeros are not significant. Is that point understandable? Okay. For a number which is less than 1, this number is less than 1. Okay. The zeros to the right side of the decimal point and up to a non-zero number, whatever is there, they are not significant. Okay. You might ask me, sir, these zeros, you called them as significant. Why is it so? After the decimal point for a number greater than 1, it generally represents, okay, it generally represents the least count of the measuring instrument. In that reading 4.700, it tells me that I have got an accuracy up to the third decimal value. 0.001 is the least count in this case. That is why the terminal zeros are significant here for a number with a decimal point. Okay. So you can also understand the importance of significant figures. For a number greater than 1 which has got a decimal value, the zeros at the end or the terminal zeros are significant because they represent the least count of that measuring instrument. Okay. Now let us move to one important concept which is regarding the mathematical operations or arithmetic operations with respect to significant figures. Now if I have to add two significant figures, subtract two significant figures, multiply two significant figures, or maybe divide two significant figures, how should I do it? What will happen to the last decimal point? Let us have a check. When numbers are added or subtracted, the number of decimal places in the final result, okay, the number of decimal places in the final result should be equal to the smallest number of decimal places of any term. Say for example, I have something like this, 1.72, 1.69, okay, and then I have 1.111. I have to add these three numbers. What will happen? I will obviously add it like this, 1, 12, 1 carried, 8 plus 6, 14, 15, 1 carried, 4. I'll get an answer like this, 4.521. Now what does this rule says? The rule says in the result, okay, the decimal places should be equal to the smallest number of decimal places. If you observe these terms, I have 2 places after decimal point, 2 places after decimal point, and 3 places after decimal point. So in the term, the minimum number of digits after the decimal point is 2. This rule says that whatever is the result that I am getting, I must be having only 2 decimal places. So I have to somehow remove this one. Is that understandable? Whatever is the smallest number of decimal places after this decimal point, that should be considered while writing down the result. Whether it is addition, subtraction, multiplication or division, the rule stays valid. See, I am adding 436.32 and 227.2. Here you can observe there is only 1 digit after the decimal place. Here there are 2 digits. Ideally, my answer is 663.52. But what am I doing? I am leaving out the last decimal and writing only 663.5. Is that understandable? I have to consider the minimum number of digits after the decimal point in the terms that I am operating. Operating means I am either adding, subtracting, multiplying or dividing. Similarly, in this equation, ideally my answer was 0.0034, but because I have only 3 decimal points, I am writing it as 0.003. Similarly, even while multiplying or dividing, I will follow the same rule. Minimum number of digits in the terms that I am multiplying or dividing. Here what needs to be understood is, I am only taking that 1 or 2 digits after the decimal point into consideration. What do I do with the last number? There is 2 here, there is 4 here, there is 5, 2 here, okay? There is 7, 8, 3, 3 here. What should I do? Should I directly drop it out, or is there any method by which I can take that into consideration? Here, I'll use a concept called rounding off the uncertain digits. As I told you, the last number in the measurement is always an uncertain digit. How do I round it? Okay, we have certain rules using which we can round it off. What are those rules? If the digit to be dropped, is in a number is less than 5, please understand, I am always speaking with respect to 5 whenever I am rounding off any uncertain digits in a significant figure. If the number to be dropped is less than 5, then the preceding digit remains unchanged. Say for example 1.344. I have to drop the last number, which is 4. The rule says that if it is less than 5, I can simply drop off this number. So the remaining significant value is 1.34. Because the last number to be dropped was less than 5. Now, let me take another example. If the digit to be dropped in a number is greater than 5, okay? If it is greater than 5, what do I do? The preceding digit is raised by 1. The preceding digit is raised by 1. Let me take the example of 1.346. The digit to be dropped is 6. 6 is obviously greater than 5. What do I do? The preceding digit, which is 4, is raised by 1. So the rounded number becomes 1.35. It was 1.346. I have to drop 6. What do? I increase this 4 or raise it by 1, which becomes 1.35. So the rounded off value becomes 1.35. Now it is very clear what I have to do when I have to round off a number. If it is less than 5, I simply drop it off. If it is greater than 5, I will raise the preceding digit by 1. 2 cases. Now what happens if the digit is exactly 5? That is an interesting case. If the digit to be dropped in a number is 5, if you have to drop a digit which is exactly 5, what do? I have 2 cases here. Okay, the preceding digit remains unchanged if the preceding digit is even. Take the example of 1.345. In this number, the preceding digit of 5 is 4, which is even. If it is an even number, then I simply drop off the last digit 5, which leaves me with the answer 1.34. Okay? If the number to be dropped is exactly 5, I look at the preceding digit. The preceding digit, if it is even, I simply drop off that 5 and take the remaining answer. Now, next case. If the preceding digit is odd, then once again I raise it by 1. Suppose the value was 1.375. I have to drop off 5, round off 5. I look at the preceding digit. The preceding digit is 7. 7 is an odd number. So what do I do with the odd number? I have to raise it by 1. So the value will be 1.38. Okay? Is that understandable? Let me just give you a quick recap. We studied about accuracy. We studied about precision. We studied about least count. We studied about errors in measurement. While we studied all these things, we understood that whenever we measure something and get a value, there are certain terms called as significant figures. Those figures which are important to us. Okay? So under significant figures, we understood that there are 2 parts. The reliable digits and the uncertain digits. Okay? And then we understood what are the rules with which we can get the significant figures, number of significant figures in any measured value. We had 5 rules. We checked all those things. Then we understood what we have to do if we are doing any arithmetic operations on significant figures. Ultimately, we understood how to round off the uncertain digits in any measured value. Okay? Have a wonderful learning experience. Thank you.